Hello everybody and welcome to exercise 6 on page 102. Let's take a minute and just read this exercise together. So they're starting us off with a definition saying that an element A in a ring R is called idempotent if A squared equals A. So it's an element whose square is equal to itself. And the first thing they'd like us to show is that if A is an idempotent element in Zn, we'd like to show that 1 minus A is also idempotent. Okay, so we're going to do that by direct calculation here using this definition. Okay, so we're assuming that A is idempotent. That means that we're making the assumption that we've got an element A whose square is equal to itself. Okay, we want to show that 1 minus A is idempotent, which means that we want to show that 1 minus A squared equals itself, 1 minus A. All right, so let's start with 1 minus A squared and see if we can show that that's really the same as 1 minus A. Okay, so first, by definition, 1 minus A squared is just 1 minus A times itself. Okay, and then we're going to use the distributive properties of a ring, basically. All right, so if you think of this as kind of being one element grouped together, 1 minus A, okay, we're gonna take the 1 and the A that you see over here and just distribute that through. So this can be written as 1 times 1 minus A times 1 minus A. Okay, we know that distributive properties hold in any ring. Okay, and then we'll use the distributive property again to take the 1 and the A that we see here and distribute those through. Okay, so we're going to get 1 times 1 as 1, minus 1 times A as A, and so on down the line here. And then minus A times minus A is positive A squared. And I'm just going to make a remark. What we're really using there is theorems from back in chapter 12. Okay, so let's see what we've got here. 1 minus A, that's minus 2A, but what about the A squared that's sitting here? What do we know about that? We assumed that A squared is equal to A, so that A squared is really just A. And if we do the arithmetic, 1 minus 2A plus A is just 1 minus A. Okay, and notice where we started and where we ended. We started with 1 minus A squared, and we showed that it's equal to 1 minus A. That's what it means for 1 minus A to be idempotent. Okay, and that is part A. And if we scroll to the second page, there's a part B to this problem. Okay, so now they'd like us to suppose that R is an integral domain and to determine all possible idempotent elements of R. Okay, supposedly we're going to be able to make a list of all of them. All right, well, what was the definition of an idempotent element again? Okay, it was an element where its square is equal to itself. So let's suppose that that's true. Okay, and maybe be a little bit more careful with our language here. So let A be an R and A squared equals A. Okay, we're just going to see where that assumption leads us. All right, well, if A squared equals A, then we can subtract A from both sides. Okay, and get that. And we can also do some factoring here. Okay, now remember, we're in an abstract ring here. And so we need to make sure that these steps that we're doing, I mean, there would be no problem doing these in the real numbers, but can we get away with doing this in an integral domain? Okay, we can for two reasons. So one thing we used was the distributive property, and the other thing is because we're in an integral domain, we know that we have a unity element, so that number 1 exists. Okay, it's important to realize that, though, to make note of it. So the element 1 in R exists. Okay, because R is an integral domain. Okay, we know that some rings might not have unity elements, but an integral domain always does. Okay, now, here comes kind of the critical step. So we've got a times a minus 1 equals 0. Let's clear a little clutter away here. And so if this were a problem that we were doing just in ordinary algebra, in an algebra class in the real numbers, we would look at this and say something like either a equals 0 or a minus 1 equals 0. That's kind of what we'd like to be able to say. The question is, can we say that here? And if so, why can we say it? Okay, well, the key to letting us do that, okay, I'm going to erase it and come back to it in a second, is that we are in an integral domain, which means that there are no zero divisors in this ring. Okay, so since R has no zero divisors, we know that when we have a statement like this, two things multiplied together that give us 0, it's not possible for both of those numbers, a and a minus 1, to be non-zero. At least one of them has to be 0. Otherwise, we'd have zero divisors. Okay, so the fact that a times a minus 1 equals 0 does imply that either a equals 0 or a minus 1 equals 0. Okay, and if you take those two statements, we can take the second equation and just add 1 to both sides, and we get a equals 1. Okay, and so what have we really shown here? Well, we've shown that the only two idempotent elements in this ring are 0 and 1. The additive and the multiplicative identity, those are the only possibilities. Of an integral domain. Okay, so maybe an interesting exercise for you would be to see if you can find a ring that's not an integral domain, and see if you can come up with an example of a ring where you've got more than just 0 or 1 as your idempotent elements. That is possible, but only if the ring that you have is not an integral domain. Okay, so you might just try that experiment.